Okay, let's move on to next topics. Let's estimate the plasticities by using atomic limits, mostly done for fine-grained soils. So in week 3, we are going to conduct laboratory tests, say simple soil identifications. You touch on it and smell it, and then you can feel it by your fingers, and atomic limit tests. Don't miss out. So here is pop questions, and then I will open these pop questions. You can navigate our X sites, and then you can go to the quizzes, and then you can click on Engineering Geology Soil Mechanics Week 1 quiz. Let's do it. The question is, atomic limits are kinds of density or kinds of water contents representing plasticity of clay or sand. Hmm. Are you guys find this quiz? Can you find this? Just one simple question, 100 marks. Make sure that this is not graded, just the um, this simple pop-up quiz. Wow, first winner for 100 marks is the Huang Kaiji. Only 9. How come our online is the 78? Okay, good. No lah. Don't be scared of the things. I'm not graded this. Okay, next case probably just 0.1, only 1 point, not 100. I strictly follow this propose. Don't hesitate to attend the pop-up quiz. Pop quiz. Yes, the atomic limit is kind of density and representing plasticity of, oh, sorry, kind of water contents and the representing plasticity of clay. The mechanical behavior of fine-grained soil is linked to four distinct states: solid, semi-solid, and plastic and liquids in order of increasing water contents. Clay minerals are source of the plasticity in soil because the clay contains some water due to their structure, mineral structure, right? Gibbsites and silicates, they're repeatedly stacked up, bonded by different types of ions, and with a large specific surface. So in other words, clay attracts waters on the large specific surface. So if clay mineral particles are present, we expect considerable deformation with respect to water contents. The plasticities describe the ability of soil to deform without any cracking and crumblings. It being clay mineral exhibit plasticity behaviors which make clay and silts differentiated. What about the coarse grained soils shows plasticities? Yes or no? You can take a look. This is the covers and gravels and a bit of sandy soils. It looks coarse grained soils non-plasticities. Yes, no plasticity behavior. The atomic limit is kind of water content. This water content governs the clay mineral behavior in terms of mechanical behavior and hydraulic behaviors. How do we define the water contents in the soils, which is the ratio of the mass of water in the soil to the mass of solid particles? Depending on the water content, the soil may exist in one of the liquids, like a slurry. Looks like a slurry, and semi-solid and solid state. They are same materials, but different water contents, right? Very, very low content, high water contents. With the high water contents, it flow like fluid, liquid, and moderate water contents. It looks like very a bit sticky, and then looks like Play-Doh, and then leave it for 10 days, 20 days, waters constantly dries up and looks like solid. It is solid, but I can't see any cracks. Still, this is the semi-solid, something like that. When you find cracks, this is the plastic behavior. If the water contents of the soils is gradually reduced, the clay states will change from liquid to plastic to semi-solid to solid. At the same time, gradually their volume being reduced until the solid state is reached. So this atomic limit indicates water content, showing the transition of states of soils. Let's consider the soils initially in a solid state. That is the dry, quite hard. Even we can say partially saturated soil, right? And with the increases in water contents, we can pouring water, added waters. These solid states start to transition to plastic states and liquid states. This each boundary water content of the each state is at the boundary limit. Boundary here, the liquid limit. Here is the plastic limit. The differences between a liquid limit and plastic limit is the plasticity index. Plasticity index, the differences. By prof, why need this kind of the boundary of water contents? First one, better understand of the clay. Second, we can classify our clay into a bit more specific group. Plasticity index is the liquid limit minus plastic limits. Hi pro, why not plastic limit minus liquid limits? Just think. Liquid limit, it means liquid to plastic. It means high water content. Plastic limit is plastic to solids. It means relatively lower water content, right? Just simply bigger value minus smaller value. This is the plasticity index. So when you conduct lab tests later on, you might weight soil mass and water mass in the soils after your atomic limit tests. So water content tests. We take a soil sample from your, right after your atomic limit tests. We can follow this process. Please make sure that a plastic container should be used to carry the soil sample to the lab to avoid moisture loss. So right after your atomic limit test, you can take the soil samples and then weight it and then put it on oven. Immediately, we reduce the air. This is a quite common sense. In order to get water itself, weight of water and weight of dry soils, we follow this. The procedure, sometimes the mixed, the order is different, but the main concept of the water content is to get water weight and dry soil weight. Now, in order to determine the liquid limits, we have roughly, famously, two lab apparatus: four-cone tests and Casagrande tests. When I was in the college time, I used to use Casagrande apparatus. Very empirical way, and then workmanship affect the result. But recent year, the four-cone test is easy to learn and then quite consistent results. obtained. So our school equipped for contests. So I will focus on for contests. And then if you are interested in the Casagrande method, I can provide more additional data. So this is the for contests. A for contest appears to offer a more accurate and then less prone to operate errors. In the forecast test, this cone with an angle of 30 degrees and then total mass of 80 grams is suspended above and then just in contact with soil sample. Something like that. This soil and cone is just contacted or small gaps. And this cone permitted to fall down 5 seconds. And then water contents corresponding to a cone penetration of 20 mm defines liquid limits. So in order to draw this straight line, you're supposed to have at least 3 points and then draw the straight line and you can visit 20 mm and then read off water content. Based on this sample of the curve, the liquid limit is around, here is 35, 36, 37. For me, 37. For you, 30.7.5 is okay. The sample preparation is important to have the homogeneous sample. So you fill the cup 1/3 and then remove any air bubble by tapping the cup and then fill up again the cup all the way. And then as mentioned before, we need 4 or more tests at a different water contents. So in our lab, Dr. Joel prepared different water contents soil samples. You bring your 3 different cups and then fill up all the cups and then test it. And then you plot it, and then draw the straight line. So each test has the different water contents. So you can get more than 3 points like this and draw the straight line to capture water content corresponding to 20 mm penetration depths. Then when it comes to the plastic limit tests, it is more like an empirical test as well. The plastic limit is determined by rolling a small clay sample into threads and finding a water content when the threads approximately 3 mm in diameters will start to crumble like this. You roll it, roll it, roll it, make it exactly 3 mm in diameters. Still, it looks continuous. It means so much water in the soil. So you can make a ball again and dry up, hand dry. You can dry up again, and then roll up again. And then you make it 3 mm in diameter. Wow, now start to crumble, start to break each other's. It means this water content is your plastic limit. After this, we can figure out our soil locations. I mean soil groups. the plasticity index is LL minus our plastic limit. Let's say we obtained a result with the liquid limit is 50% and plasticity index is the 20%. Oh, sorry. LL is 50, plastic limit is 20. So it means plasticity index is 30. So 50 and plasticity index 30 here. It means that this soil is clay. Let's say 50% and the plasticity index is around 10 is this soil is sint. And then your soil is more toward left side, clay with low plasticity. And then your clay located right hand side, your soil is clay with high plasticity. That's why we need to get Avogadro limit to reclassify, refine our clay soils groups. So I'm gonna show you how to do liquid limit tests.
Cone penetrator. Penetration cone and sample cup. Clay samples. Containers. Label containers. Weigh the containers and record the weight. Fill cup with sample layer by layer. Tap to remove air bubbles.
Do not tap on desk at the floor, on the floor.
Wait. Too noisy. Better to do it on the floor. Level the top face. Check height of penetrator adequate for cone plus cup. Attach the cone. Turn knob to minor, adjust height. Check cone tip is just touching the top face of sample. Ready. Make sure digital dial gauge is touching cone holder. Turn on and tear. Turn on power. Set 5 seconds. Hands off from cone. Press start. 5 seconds is up. Push dial down gently. Record penetration to nearest millimeters. Pull dial up gently. Bring cone up. Remove cup and clean cone. Repeat test for 2 times. Remove cone and keep in box. Take sample for moisture content test. Empty sample from cup and clean cup. Repeat penetration test for all other samples with various moisture content. Sand moisture content samples for oven drying. Come back next. Data take reading. Turn on power and clean up.
Next test is another atomic limit test for plastic limits.
Wear glove if necessary.
Now it's too wet.
If clay is too wet, use paper towel to reduce moisture content. Let's try rolling. Almost 3 millimeters, but not breaking up yet.
Hand dry.
Starts to crack.
Wow. Start to crumbles.
Prepare more samples. Cover sampler stove, prevent moisture loss. Time for oven drying. Come back next. Data take reading. Reminder: wash hand with soap return and use samples housekeeping.
I'm asking again, why do we need to do the atomic limit tests? Reclassify our clay soils. Why do we classify our soils? Have you think through these questions? When you have a soil samples, basically we check soil's colors and smells and shape and textures and composition of particles. This is our first lab before conducting atomic limit tests. And then we put it all together, we classify our soil and describing their engineering behaviors. We classify our soils. We have so much soils out there and bringing it to our lab and then classify. Oh, this is the sand, this is the clay, and high plasticity, low plasticity, and gravel sand, silty sand. We form a group, and then the soil in that specific groups shows similar engineering behavior. That's why we have to classify our soils to better understand. This is our rule, our rule. And every engineer in the world understand the specific soils engineering behavior. So what is important is that soil classification provide us general guidance about engineering properties of soils and engineering behaviors of the soils. So we have three common methods to classify our soils. One is the Unified Soil Classification System, so-called USCS. USCS. Second one is BS, British Standard. Our Singapore, we strictly follow Euro codes coming from Europe. So it means that our contractors use British standard soil classifications. But USCS is coming from the ASTM. They are quite similar, also very famous in the world. These soil classification systems quite similar to decision tree models. Hey, we have soil samples. Is it coarse? Is it fine? Yes, of course, this is the coarse grain soils. Is it the gravel is majority or sand is majority? Yes, sand is majority. In your sand, is there any fine materials? Yes, I have. It is silty sand, something like that. So these figures explains the particle size with respect to different standard. British, USCS, Asheto, and ASTM. The USCS and then Ashetos and ASTM, they are quite similar, and the British are a bit different. But I think there's no perfect systems for describing soils. So normally USCS, ASTM is widely used, and the BS is commonly adopted in Europe code. So our local contractor prefer the BS systems. In the practical things, BS is quite common, and then in Singapore, and we also have a local standard. Singapore National Annex define specific soil classifications only for Singapore soils. In Korea, we have different soil classifications, but we follow ASTM, USCS. So according to USCS, we have fine grain, coarse grains, the soil particles according to the specific numbers, 0.075 mm, and then 4.75 mm, and 75 mm. And then from the sieve analysis, right, we are able to figuring out the proportion of gravels and sand and fines. From the figure, we also calculate the uniformity coefficient and coefficient of curvature based on D10, D30, D60, right? That's why we discussed about sieve analysis, hydrometer analysis, and atomic limit tests to classify our soils. And the classified systems, we have ASTM and British. According to the USCS, Unified Soil Classification Systems, deals with coarse and fine grain and organic soil and pits. And according to our sieve analysis results, R is the retained above 200 sieve. F is the passing through 200 sieve. This is the opposite concept. Retained one is more than 50%. It is coarse grain soils. Once this soil is forced on coarse grain soil, we follow this specific guideline criteria. The gravel fraction is greater than sand fractions? Yes, it is gravels. We give them first letter G and so on. Silt and clay fractions. We can see it laterally. And then finally, we have specific group here. well-graded gravels, poorly graded gravels, silt gravels, poorly graded sand, silty sand, something like that. So in the international conference, I'm a speaker. Now I'm dealing with Singapore soils, but I can say Singapore clay is something like clay sand with gravels. So I can say this way, other attendants and then the international researchers roughly understand, and they expect our Singapore's clay's engineering behaviors. That's why we need to classify our soils. And this is fine grained soils. In the fine grained soils, we need atomic limit results, liquid limits, and even plasticity index. In laterally, we can see something like that. Okay, Singapore clay, something like um, something like, for example, sandy ring clay with gravel, silty clay. So the wording, when it comes to the coarse grained soils, these two first letters are combined with other symbols expressing grading of the characteristic. S is sand, G is gravels. P is poorly graded, well graded, and then M is silt, and C is the clay. This table tells you how to classify the coarse grain material more specifically according to our group symbols. And for the fine grain soils, we have C is clay, M is silt, O is organic, PT is a pit. And the L is the low plasticity, H is the high plasticity. How do you know? From the atomic tests, these charts. And then we can specifically combine these two symbols. CH means clay with high plasticity. That's all. Easy to understand the expected engineering behaviors. This is the plasticity chart consisting of A line and center line, worldwide standard, by using atomic limit tests. Even we have a dual symbols. This is for very special soil types. But even if they have a dual symbols, the engineering behavior quite similar to nearer soil classifications. CL-ML is dual, but I don't think their engineering behavior quite different with ML or OL. Only different thing is the liquid limits. The CL-ML is a little bit lower side of the liquid limit, and then plasticity is quite specific, 4 to 7 only. But the liquid limit, plastic limit is quite empirical, right? Something like that. In for contests, how do you control these micro numbers, 4 to 7? There should be human error. That's why even if we have a clear charts in terms of specific numbers and our soils, anytime falls on dual symbol here, 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 here. You need to understand these uncertainties. Concrete, steel, they have exact solutions. So concrete grade 50, exactly 50. So we design mixtures to get specific grades. And then their performance shows as we expected. But soil is totally different. Everywhere we have different soils. And all experiment quite empirical. That's why someone say, wow, that's why soil mechanics is so interesting. But some student blame, so difficult. How do we guess that engineering behavior? I totally don't understand. I can't imagine that behaviors. But in a positive way, you accept our soil has a very, very, very big uncertainties. This is a BS chart. This is the ASTM USCA's charts. All are similar, technically different, very similar. This is the soil classifications bite-sized video for the general things.
There are numerous amounts of soil present on the surface of Earth, each containing soil particles of different sizes, shapes, and composition. If we classify and categorize soils, it will be convenient for us to study them. We arrange the soils into different groups, such that soils in particular group have similar behavior. This arranging of soil is called classification system of soil. Any classification system must provide us the information about the expected engineering properties of a soil. It works as a language of communication between engineers. Classification is done so as to convey the same meaning universally. An engineer in one country classifies a soil as SW, then another engineer in some other country should be able to understand what kind of soil the other engineer is talking about. Of course, we need to do a detailed soil investigation and testing for the complete knowledge of engineering properties of soil. But a classification system provides an idea about soil's engineering behavior. Any such classification should be simple to use and should have limited number of groups. Generally, we classify soils as cohesionless and cohesive, or coarse-grained or fine-grained. But these terms are too general and they certainly do not classify a soil when it is a mixture of different soil grains in different proportions. Soil grain size has a great influence on the behavior of soils. So, most soil classification methods use particle size as a basis to classify the soils in groups. We generally classify the soils based on the particle size into four broad groups: gravel size, sand size, silt size, and clay size. Gravel sized particles being the largest and clay sized being the smallest. Do notice that we have written silt size and clay size, not the silt and clay, because these are the ranges of size, not the actual size silt and clay, which exhibit properties of plasticity and cohesion. Not all the clay sized particles are clay particles. A big rock boulder has some rock mineral composition which is different from clay minerals. Such big rocks, because of weathering, transforms into smaller particles. Their size may become as small as clay particles. But such particles do not exhibit plasticity as they do not contain the clay mineral and certainly are not clay, but definitely clay-sized particles. Clearly, we notice a system of soil classification purely based on particle size may be misleading, particularly for fine-grained soils, as their behavior depends on the plasticity characteristics, not on their particle size. But we must keep in mind that for coarse-grained soils, their particle size is of great value, as their behavior primarily depends upon it. Soil classification system. It was first developed by Casagrande and later it was modified by Bureau of Reclamation and the Corps of Engineers of the USA. This system has also been adopted by American Society of Testing Materials, ASTM. It is the most popular system for use in all types of engineering problems involving soil. This system identifies soils primarily as coarse-grained, fine-grained, and highly organic. Coarse-grained soils are classified on the basis of their grain size distribution, and the fine-grained soils, whose behavior is controlled by plasticity, are classified on the basis of their plasticity characteristics. According to this system, coarse-grained soils are those which, when sieved, more than 50% of their mass is retained on 0.075 mmC. It means more than 50% of the soil mass contains particles which are larger than 0.075 mm, could not pass the 0.075 mmC. If more than 50% of the soil material passes through this sieve, then the soil is classified as fine-grained soil. This soil will contain more than 50% of its soil mass made up of particles which are smaller than 0.075 mm. These are some symbols used in the system to classify the soils. G is for gravel, S is for sand, M for silt, and C for clay. O is organic, and PD is for peat. Peat are highly organic soils. It also uses symbols W for well graded, P for poorly graded, L for low plasticity, and H for high plasticity. Coarse-grained soils are further divided into two categories. We further sieve our obtained coarse-grained soil part using 4.75 mmC. This sieve has larger openings than that of which we used earlier. What we are trying to do is to separate the coarser part of the coarse-grained soil from the finer part. If more than 50% of this coarser fraction of soil is retained on this 4.75 mmC, then soil is designated as gravel and is denoted with letter G. And if more than 50% of coarser fraction of soil passes through this sieve, soil is called sand and is denoted with the letter S. A soil labeled as gravel has more than 50% of coarse-grained particles, which may also contain some percentage of sand particles and some of fines. If the percentage of these fines in this gravelly soil is less than 5%, and if the soil is well graded, that is, soil contains all kinds of soil particles, then it is classified as well graded gravel, and it is represented by symbol GW. If the soil is poorly graded, then it is poorly graded gravel with the symbol GP. Similarly, SW and SP go for the sand. Now, if the percentage of fines in the soil is greater than 12%, and if it is gravel soil and contains silts as its fine, it is designated as GM. G for gravel and M for silt. GC if the fines are clay, SM if soil is sand and contains fines of silt, and SC if sand contains fines of clay. If the percentage of fines in coarse soils is between 5 to 12%, then we use dual symbols to represent them. A well-graded gravel having 8% of silt content is represented as GWGM. Similarly, for poorly graded sand having 9% clay content, the symbol will be SPSC. And similarly, others. It was the classification of coarse-grained soils. Now we look into the classification of fine-grained soils. Fine-grained soils are divided on the basis of their liquid limit and plasticity properties. Casagrande plotted a plasticity chart, a graph of plasticity index of soil and its liquid limit. It is plotted from the experimental results of soils collected from different parts of the world. He separated clay, silt, and organic soils using a graph he called A-line. Equation of this A-line is given as this. Clay soils sit above A-line as they have high value of plasticity index because of the clay minerals present in them, where the silts and organic soils lies below this A-line. Unified system classifies fine-grained soils in two categories, as soils having liquid limit less than 50% and soils having liquid limit greater than 50%. So in the graph, we plot a vertical line at liquid limit 50%. According to this system, fine-grained soils lying to the right of this line have high liquid limit and are represented by symbol H. If the soil in this part is clay, then symbol used will be CH. If it is silt, then MH, and for organic soil, it is OH. Soils lying to the left of this 50% line have low value of liquid limit. So they are represented by symbol L. Soils in this part are described similarly Cl, Ml, and Ol. This line already separates clays from silt and organic soil. Now to distinguish between the silt, which is inorganic soil, and organic soils, we use oven drying. We note down the soil's liquid limit before and after oven drying. If oven drying decreases the liquid limit of soil by 30% or more, the soil is organic and it will have symbols OL or OH. And if the decrease in the liquid limit is less than 30%, soil is inorganic and the symbols will be ML or MH. A U line is also defined as the upper limit of the correlation between the plasticity index and liquid limit of soil. If the test results of the soil fall above U line, then results are considered faulty and experiment should be repeated. Equation of the U line is given as this. It was the classification of fine-grained soils. Lastly, the third category unified system defines is highly organic soils. We can identify them by simply looking at them. These soils are termed as peat and are designated by the symbol PT. These soils are not subdivided. And now we can complete our unified soil classification system chart. Symbols used in the unified system are more descriptive and are more easily remembered. This classification system has